All right, we are part of the way through section 2.1. This is our intro video for our next section. We're going to be talking about differentiability and continuity. Let's talk about differentiability for just a minute here, what that is. This is basically, what all this does is it addresses whether the derivative exists or not at a particular point. It addresses whether the derivative can be found or not at a point. So I want to introduce another form of the derivative to you here. Limit as x approaches c of f of x minus f of c over x minus c, that's equal to f prime of c. Sometimes folks get a little uncomfortable because this does not look exactly like the other definition of the derivative we looked at, the one with the h, or maybe the one with the delta x. But I just want to point out some commonalities here. Please notice that this right here is the difference quotient. It is the difference in y divided by the difference in x, and so that means that's a slope, right? That's an average slope. And then our limit here is such that the denominator is forced to go to 0. So anytime you have the difference quotient and there's a limit put on it so that the denominator goes to 0, that's the derivative. And so we're going to talk about that a little bit here in this section. The next little point here says for a function to be differentiable at a point, the function must be continuous and the derivative from the left and the derivative from the right must be the same. So one way of looking at that would be to say this: limit as x approaches c from the left of our difference quotient must equal the limit as x approaches c from the right of our difference quotient. This is just saying that the derivative from the left and the derivative from the right need to be the same. So let's see what that looks like on a graph. So if you take a look at this graph right here, I would say let's focus on a couple of different points. Let's focus on this one right here first. That's our c value. And so I would say that as we approach c from the left and as we approach c from the right, we can see, at least that it appears from a graph, I mean a graph is always some kind of an estimate, that as we approach that from the left, as we approach that c value from the right, it looks to me like the slope to the left of that point and the slope to the right of that point are the same. So I would say that c is a point of differentiability. We could actually find the derivative at c. But I think over here on the left, I'll call this point D, we have something else entirely. I think that as we approach D from the left and as we approach D from the right, we have a very, very different slope. We have a very, very different derivative. And so I would say point D is a point that is not differentiable. We'll get a little more detailed about that here in a second, but point D would not be differentiable. So let's take a look at 3 different situations for a function to be not continuous. All right, example number 1, a function that is not continuous at x equals c. So if a function is differentiable, that means that it is also continuous. And you can see with this function, this is that greatest integer function we've looked at, I believe, before. You can see that basically every integer value, so at 1 and 2, 3, 0, -1, -2, at each of those points we have a point of discontinuity. Therefore, at each of those points where f of x is not continuous, f of x would also be not differentiable. All right, example number 2, a function with a sharp turn or cusp at x is equal to c. So I'd say in this case our c value is 2. I think 2 is a point of non-differentiability. So you can see that it's labeled on your picture as such. The slope on the left side of the graph is -1, the slope on the right side is +1. So I think what we could write here for this would be to say the limit as x approaches 2 from the left of f of x minus f of 2 all over x minus 2, that's equal to -1. But if we do the exact same limit from the right, we actually get +1. And since -1 obviously does not equal +1, I'd say that x equals 2 is a point of non-differentiability. You've got the sharp turn or the cusp. This is the type of justification we're looking for here. To just say that a function has a sharp turn or a cusp, that's a good description, but it's not a justification. It's not actually a good reason to justify your answer. And then finally, our last case of points of non-differentiability, different examples, is a graph with a vertical tangent line at C. So in this case, our C value is right here, 0. That's where we have a point of non-differentiability. We have a vertical tangent line right there. You can kind of see it represented graphically, but you can see that the graph gets very, very steep there, perhaps vertical. Later on, we can actually prove that this is the case. But this vertical tangent line would also cause the function to be not differentiable there. Let's talk about why that is. Remember, the derivative is the slope of the tangent line. So I'll put this over here. Derivative equals slope of tangent line. And what is the slope of a vertical line? That is a does not exist. So if the slope of a vertical line doesn't exist and your tangent line is vertical, that means the slope is d/e. That means the derivative doesn't exist either there. So that's our final case. So the three cases were if we have a point of discontinuity, or if we have a sharp turn or a cusp, as well as a vertical tangent line. Those are the three cases that create a point of non-differentiability. I want to finish this video off by just talking about the relationship between differentiability and continuity. If a function is differentiable, then it is also continuous. And so this is a little phrase we'll use from time to time. Differentiability implies continuity. So if the start of the question tells you that some function is differentiable, then you can assume that that function is also continuous. But the reverse of that is not true. Continuity does not imply differentiability. So I want you to take a second and think of a function that is continuous at all points, but not differentiable at all points. So pause the video, think about it if you want. I'm going to go ahead and fill it in right here. I think some classic examples would be the absolute value function. F of x is equal to absolute value of x. And then really that one we looked at just a second ago, f of x equals x to the 1/3. That's not a very good graph. F of x equals x to the 1/3, something like that. We have a point in there where the function is not differentiable, but you can see both of these are continuous. There are many different examples of this. Maybe you thought of different ones, but these would be two classic cases that we've looked at here today. So we'll continue this on when I see you guys next time in class.